All right, we are looking at lesson 1 in our unit 5, our systems of equations unit. So we're looking at the big race Olympic qualifiers. We have 6 different participants: Lisa, Carly, Rob, Craig, Sherry, and Chelsea. And we are going to graph each of their equations or their path of their race onto our coordinate grid here. So first thing I'm noticing is in some of the descriptions here, we have seconds and we have meters. So let's go ahead and label our X and Y axis. Our X axis is always our time, our independent variable. This is going to be seconds. And then our Y axis is going to be meters, distance traveled. Okay. So first, let's go ahead and graph Lisa's equation. We're going to do y equals 1/2 x plus 2. So let's do that first here. This is looking like Lisa got a 2-meter head start. So when the race was at 0, she was already at 2 meters. And then she's traveling at a slope of 1/2. What that means is for every 2 seconds, she's traveling 1 meter. So I'm going to place several points on my grid here. If you want to, you can just go all the way to the very end, or you can pick up a ruler and connect them. I'm going to use the same color here. And I'm going to color code my graph. So this is going to be Lisa's path. If yours is color coded or not, I recommend at the very end of that to write the name of the participant next to that. So we got Lisa's graph. Let's try one more. Let's try Carly's graph. Let's do pink here. So for Carly, Carly started 4 seconds after the race began. So I'm going to put Carly here. So after 4 seconds, then she started. So at 4 seconds, she was still traveling. She had 0 meters traveled. Okay. And she travels at a rate of 3 meters every 4 seconds. So 3 meters, I'm going to go up 3 meters, 1, 2, 3, and 4 seconds, 1, 2, 3, 4. I'm going to get rid of those dots there. Okay, I'm just going to put this here. And then she's traveling 1, 2, 3 meters, 1, 2, 3, every 4 seconds. I'm just going to use those lines. I'll go ahead and connect them. And then at the end of that line, oh wait, I want to connect them. Let's keep my color coding here. I'll connect them with a pink line. And this is why it's helpful to be accurate with our lines so we can make sure they're intersecting at the proper point. We're attending to precision. Let's go 1, 2, 3, 1, 2, 3, 4. See, my line was not perfectly accurate. I'm going to erase some of these. There we go. 1, 2, 3, 1, 2, 3, 4. All right, so now that I did those extra lines and you can see, or those extra points, you can see my line actually wasn't too accurate. So I'm going to erase this line here and I'm going to redraw that in. Because we might have to have a collision course of some point where they're intersecting each other. So the more lines you draw in, the more accurate, or the more points you draw in, the more accurate your line becomes. So this is Carly. Okay, go ahead and graph a line for Rob. We got y equals 5/6x. There's nothing being added after that, so remember that would be like, you could almost imagine plus 0 here. Okay, and then 3-meter head start. So 3-meter head start, or that would be our y-intercept, and then we've got a distance of 1 meter every 2 seconds. So up 1 meter, 1 meter every second. So 1 to 1. So that's like a y equals x line. There we go. And then we've got Sherry's line. And then lastly, we've got, which is already in slope-intercept form, so we can graph that. And then lastly, we've got Chelsea. Chelsea started 5 seconds after the race began. So at a disadvantage there. And rode 5 meters every second. That looks pretty fast. So I would start at 5 here, and then 5 meters for every 1 second. So up 5 to the right 1. Okay. That's your first step, graphing all of your lines on the coordinate grid. Now, our second step is to determine who won the race and how we know. So what we're trying to do is the race is 25 meters. So 25 meters this is the distance. Okay. Now you can see here that Carly and Lisa didn't get to 25 meters. Okay. So we are looking for who got to this top part of this line here the quickest. So let's see, I had a line ending, let's pretend I had a line ending here, here, and here. Well, this would be the one that was fastest because we traveled 25 meters in the least amount of time. So look at your graph, examine that, and we're looking for, I guess, the steepest line. That would be another way. Which line is the steepest that reaches the 25 meters first, okay? Then you're looking for at which point do Sherry and Craig cross paths. And again, attending to precision. So remember, this was Carly and Lisa, and I wouldn't have gotten that point accurately unless I graphed all of my coordinate points. So check the line for Sherry and Craig and see where they intersected. And then we're going to show algebraically by substituting the point of intersection into both equations that Sherry and Craig do indeed meet at that point. So we need some equations for all of the racers here. Let's go ahead and start adding some of these. Let's do Lisa. Well, Lisa's easy. Lisa's equation was y equals 1/2 x minus or plus 2. Carly. Carly is here. So for Carly, you're going to actually need to create an equation for that. Let's see if I don't have any extra space. I'm going to write my work here. So we can't, if you want to, you can kind of backtrack to see where the y-intercept would be. It's kind of like a negative y-intercept, which is kind of weird to comprehend. But the information that we know about Carly's line is we know that there's a point here at 4, 0. And we know the slope of the line is up 3 to the right 4, 3/4. So you can write the equation of this line in point slope form, y minus y1. So this is our x and our y. So it's going to be y minus y1, which is 0, equals our slope, and then x minus an x1 minus 4. If you want to, you can rewrite this in slope-intercept form. You can also get rid of this y minus 0. We don't necessarily need that because y minus 0 is just 0. But you would have to distribute. So if we want that back into slope-intercept form, y equals mx plus b, I would have to take 3/4, and I would have to multiply that by a -4. And when multiplied by a -4, it is going to be -3. So if you're using kind of a backtracking method and we were graphing this, you would say, oh yeah, the intercept here is at -1, 2, 3, -3. So you can leave it in point slope form, though I think it's okay to leave it like that. And then we've got Rob's equation, which you can write in. Craig's equation, we'll come up with an equation. Sherry's, we already have. Y equals 2x minus 2. For Craig got a 3-meter head start. So started here at 3. Well, that's our y-intercept already. That one's nice and easy. So our y-intercept is at 3 and rode 1 meter every second. Slope is 1. So I would say y equals 1x, or just x plus 3. That would be the equation for Craig. Okay. Now we want to show algebraically. So we've got our two equations. So we've got Sherry's equation and Craig's equation, and they both say y equals. So we're just going to set them equal to each other. We're going to write x plus 3 equals 2x minus 2. I'm going to bring all of my x's to one side. That gives us 3 equals x minus 2. Add 2 to both sides, and we would get 5. So hopefully the point of intersection had an x value of 5. Now to figure out our y value, we use substitution again, and we can plug it into either one of these equations. So we know y is equal to x plus 3. Oh, we're going to change x though. We're going to make x 5 plus 3. So y is 8. If you want to plug it into the other equation, you can, just to check, make sure. And 5 times 2, 10. 5 times 2 is 10. 10 minus 2 is also 8. So our y value is 8. So 5 comma 8, that should be what you got when you looked at the graph. It should also be what you got when you solved it algebraically. Okay. Now you are looking for 1 point. At 1 point, 3 competitors all meet. So there's a point of intersection there. What is that point and who are they? So what are the 3 competitors? And then name 2 competitors that never cross paths. Okay, so your answers might vary for that. And they're not crossing paths during this competition here. But eventually, if the lines keep going on forever and ever and ever, they might intersect with each other. Okay. Now on our next page, so you'll have some toolkit that you can fill in on our next page here. What we're doing is we are graphing, we're graphing a system of equations. So these 2 equations here, we're going to graph them on the same grid, and then we're going to see what the solution is. The solution is the x and y value where they intersect. Okay, so first graph, I'm going to do this in pink. Our intercept is at positive 3. A y-intercept is at positive 3. We place that here. Our slope is negative 5/3. Remember, negative is going down and to the right. So from this point, I go down 1, 2, 3, 4, 5 to the right. 1, 2, 3. And then we place a point there. And then we can draw a line that goes through those 2. And the line should go on infinitely in both directions. There we go. So something like that. And if you want to do arrows on both sides, you can as well. And then we've got our other line. I'll do this in blue. It starts at negative 3. That's this point here. And our intercept, or our slope is 1/3. So up 1 to the right, 3. Or I can just go up 1 to the right, 3, and then get rid of that point. And that would be this point right here. You can also go down 1 to the left, 3. So I'll draw in the complete line for that. And so we are looking for the point of intersection. And you might want to circle that on the graph and do my little arrows here. So the point of intersection is located right here. It is at 3, negative 2. So I would say that is the solution to that graph. Go ahead and you're going to graph the rest of the equations onto the grids here. Remember that for something like this, we've got y equals, this is almost like saying y equals 0x minus 1. So the steepness of this line is 0, right? That's a horizontal line. And then based on our toolkit, if we have lines that never intersect each other, we will not have a solution. We call that no solution. Okay. Once you get to this last page here, you're going to be graphing these. I would recommend rewriting some of your equations in y equals format. So for example, if we want this equation to be y equals, I'm going to add the 3x to both sides. When I do that, I end up with y equals 3x plus 8. Now that it's in slope-intercept form, I can go ahead and graph it. We put our first point at 8, and our slope is 3, or we could say 3/1, right? For this one here, I'm going to add an x to both sides, add an x, rewrite this equation as y equals x minus 2. So our intercept is at negative 2, and we have a slope of 1. Okay. Next one here, these ones aren't just as easy. If I subtract an x on both sides, we worked on this in the last class, we would get 2y equals negative x plus 4. Well, we need to isolate y. We'll divide by 2 on all of our terms here, and we'll get y equals negative 1/2 x plus 2. So notice that these end up being the same exact equation. So when it's the same exact equation, that means those lines coincide with each other. They're overlapping, and all the solutions for one line would be the solutions for the other line. Infinite solutions is what we call that. Okay, so you're just going to be graphing for the rest of these. We have another horizontal line. Remember, we have also a vertical line in the x equals format. So just graph the rest of these and find their point of intersection, and then make sure you write your coordinate solution as a coordinate point, your solution as a coordinate point. And do know that if the lines are parallel, you can write no solution, and if the lines are the same exact line, we can write infinite or all real numbers.